All right. So gauge theory, non-commutative principal bundles. That's what we're going to talk about. So really what I'm going to focus on is adapting to the sort of operator algebraic non-commutative geometry context, specifically spectral triples and unbounded KK theory of principal bundles, principal connections, gauge transformations, etc., etc. So shameless self-promotion of the preprint with my Dr. Bruder Bram Mesland, which you can consult in the archive. All the sort of horrific generalities are there. And certain algebraic aspects I'm sort of preparing for in a manuscript with a working title that I hope some of you will find sufficiently provocative to look forward to. But I want to make a note that given that it's 20 minutes, I really want to focus and simplify shamelessly to the easiest possible case. I want to talk about unital non-commutative principal circle bundles with totally geodesic orbits of unit length. We can handle geodesically complete non-compact spaces. We can handle compact connected Lie groups, but anything more general of that, that's an interesting matter. We can make sense of orbit-wise extrinsic geometry so that totally geodesic orbits has a precise meaning and unit length has a precise meaning. But still, this is interesting enough to handle all sorts of cases of interest, such as the irrational rotation algebra, or as a circle bundle over the classical circle, or the theta-deformed complex Hopf vibration. So, basic setup. Let's begin at the beginning. A very good place to start. Let G be the circle group, just the unimodular complex numbers with multiplication as the group operation. It's the easiest Lie group of all. Just to take that into account. It has a normalized Haar measure, which is given by 1 over 2 pi times dt, which is naively dt if you think of t as parameterizing the unit circle via angles and radians, counterclockwise. So the math frac G is a Lie algebra of G, the tangent space of the identity. Lie algebra is spanned by d by dt, which you can interpret naively. The dual is spanned by dt, which you can interpret naively, and they're dual bases. So there's a notion of having a free action of a group on a topological space. There's various ways to translate this into the context of operator algebras. It turns out that when you're dealing with a compact quantum group, all these things coincide. So I'm going to take the path of least resistance and say that a unital C-star algebra carrying the strongly continuous action of the circle is principal if and only if it's saturated in the sense of Riefel. So you take your C-star algebra, you chop it up into these isotypical components, these eigenspaces for the circle action, and then you require basically that each of these guys is a full Hilbert C-star module over the G invariance. So this is a pretty nice situation. This is a nice condition to check in practice. In other contexts, you'll see this definition due to Elwood, which is more satisfactory for other formal reasons, but they turn out to be equivalent. In any event, the moment you have a unital G C-star algebra with such a nice action, you can think of this as defining a non-commutative topological principal bundle. You have a total space, which is A. You have a base space, which is the subalgebra of G invariance. And so our most familiar cases are these. In general, the moment you have a cross product by Z, think of an irrational rotation, for instance, this canonically gives you a circle bundle, a non-commutative circle bundle. You just have this sort of the dual action of U of 1 on the generators coming from Z. So the irrational rotation algebra fits perfectly to this, and the base space there is the circle. And then there's another example, due ultimately to Matsumoto, and then analyzed, for instance, further by guys like Brzezinski and Ćaćić, the theta-deformed complex Hopf vibration, whose total space is this deformed three-sphere. There is still a vestigial circle action. Classically, you have SU2 with its maximal torus, and then the invariants are the usual classical two-sphere. But note that this algebra is a commutative subalgebra of this guy, but it's not central. And you get a similar thing here. So what I want to do is sort of kick this up a notch and talk about some kind of differential geometry. So following Kohn amongst the many other people, I'm going to use spectral triples to talk about differential geometry and Riemannian geometry, amongst other things, on such of these. So in general, let's just suppose we have a unital separable C-star algebra A with a strongly continuous action alpha of the circle group G. We'll define an equivariant spectral triple for A to be the following data. So it's the usual AHD, if you've seen this spiel before, plus a little extra. So first off, you need a covariant star representation of A. And let me just note that for our purposes, it actually turns out to be useful to be shameless about using Z2 graded objects, Z2 graded C-star algebras, Z2 graded representations, super conventions all the way. So all commutators are actually super commutators. So you have a faithful Z2 graded covariant star representation of the pair A alpha, call it the Hilbert space H, unitary representation U. You have the second ingredient is an odd G invariant self-adjoint unbounded operator on H with compact resolvent. So it has countable spectrum, finite multiplicities, clustering at infinity. And the domain of D consists of C1 vectors for the unitary representation of H. And then finally, you need curly A. You need a distinguished subalgebra of differentiable elements of A. Call it curly A. It's part of the data. And it's a dense G invariant star subalgebra that consists of C1 vectors for the G action A. That's, at the very least, I'm not requiring any kind of topological closure, except that if you convolve by a trigonometric polynomial, you stay in curly A. So this means the Fourier coefficients with respect to the U1 action stay in curly A. And then you have bounded supercommutators with D. And these are morally your exterior derivatives or gradients. And so an example to have in mind, think of trigonometric polynomials acting by multiplication on two vector valued functions on U1, L2. And then what you have this nice little first order differential operator. That's your D. And then your unitary action is just translation on basically L2, on two copies of L2. And this is an equivariant spectral triple for continuous functions of the circle with the translation action of the circle in itself. There's stuff in Brown, which people who like index theory should bear in mind. If you really, really want to dot your I's and cross your T's, you need to account for Clifford multigradings. But if this is your first time seeing this, don't worry about it. Okay. So this is your analog of non-commutative G manifolds. So what are these things good for? So this is sort of the standard spiel due ultimately to Kohn. Your G spectral triple encodes the following data. So first off, it's giving you a differential calculus, the so-called Dirac calculus. So you should think of the commutator, the supercommutator of D with A as a sort of non-commutative gradient or exterior derivative. Really, it's a Clifford action thereof. So there are fundamental conceptual problems when you try to go to like the second order of your differential calculus and so on, but first order is good enough for now. You code the spectral geometry via the heat semigroup. And this is actually a point of interface with the next talk by Marius Junge. There's a whole lot of mileage you can get from analyzing this heat semigroup, which is typically, in most cases of interest, valued in the trace class operators. So you can talk about dimension, volume, measure. The small time asymptotics become a fount of very interesting geometric information. And then there's index theory. So if you like non-commutative algebraic topology. So where these things ultimately come from, they're unbounded K cycles. They represent elements of K homology. So here you're getting something in the G equivariant K homology of A. That's what's going on. So what I want to do now is say, okay, how can we distinguish locally free and free action? How can we distinguish the non-commutative principal bundles from more general non-commutative G manifolds? So by the way, before moving on, points 1 and 2 hinted possibilities for non-commutative gauge theory. So compare the spectral action approach, which kind of sidesteps the machinery of gauge theory, goes straight to an associated vector bundle, and goes from there. So this is where things kind of sort of get new. There are antecedents in work by, for instance, Dombrowski and Ćaćić and Forsyth and Rennie, but things get all kinds of interesting when G is more general and when things get non-unital. But basically, what is this extra bit of data that you need at least to have a locally free action of G in our case, U1 for today. Well, basically you need a Clifford action of vertical one forms of, you need a Clifford, a sort of orbit-wise sort of Clifford action by one forms in G. So what this boils down to is you have an odd self-joint G invariant operator, suggestively named C of dt, skew adjoint. It squares to minus what really is going to be the length of the covector dt. So more generally, there's a vertical metric that that multiplier valued metric on your Lie algebra that you need to worry about, but here the orbits have unit length. You need this vertical one form to supercommute with everything in curly A. And then the sort of subtle thing here is that you need a sort of intrinsic compatibility between this vertical Clifford action and your Dirac operator. So morally, you need this condition. So you can define a kind of moment, mu. In general, this will be an operator valued one form on G, that whose boundedness tells you that there is a basic sort of intrinsic compatibility between this total geometry of the spectral triple and the de Rham calculus on the structure group G. So basically, you take the supercommutator of D with really C of d by dt. Is it sharp or flat? I forget which one, but you know what I mean. But you basically look at D of d by supercommutator D with C of d by dt flat. This morally ought to be covariant differentiation along your Dirac, your Clifford connection in the direction of d by dt. And you want to know that it's basically comparable to straight up differentiate the infinitesimal unitary action on H. So you need this compatibility here. You need this moment map to have bounded values. And then once you have this data, you can safely define the vertical Dirac operator. In the simple case, this just boils down to C of dt times partial differentiation along the G action in the direction of d by dt. The moment you're non-Nonunitl, this becomes more complicated. When you're non-abelian, this becomes a little more complicated. There's an extra locally bounded term encoding structure constants. And basically what this is a representation of Costant's cubic Dirac. So that's what you really want to think of more generally. But for now, you just have Clifford action by dt times partial differentiation along the unitary representation in the direction of dt. And then as sort of extra bells and whistles, it's convenient to define a kind of vertical algebra, sort of vertical Clifford, sort of the sections of the Clifford bundle of the vertical cotangent bundle, if you like, or the cotangent bundle of the orbits rather. So you basically just take the Clifford algebra generated by C of dt, take curly A together. This ingredient supercommutes with this together, really it's a tensor product. Together they generate an algebra. We'll call it V sub 1 of A, one standing for this constant unit vertical metric. And then you can close this up in the operator norm and you get a C-star algebra. And this will still be a G C-star algebra. So once you have this, you can be pretty confident that what you have is at least a locally free action of G. So now you can say, okay, I have my Dirac operator, which encodes the total space and the total geometry, the total differential calculus. I've picked out a vertical direction. Surely to God, if I subtract away this vertical piece, I've got the horizontal piece, the sort of horizontal lift of the geometry downstairs in the base space. But it's not quite so simple. You need a little flexibility. And you need the flexibility to correct basically by an odd self-adjoint correction term, which I'll unimaginatively call a remainder. So once you pick a remainder, then you can correct away and you get something you can legitimately call a horizontal Dirac operator. So d sub h with respect to z is d minus z minus dv. If you're super lucky, this is 0 on the nose, but in the commutative case, you will almost certainly never be so lucky. And instead, there's a canonical, and typically non-zero candidate coming from the commutative case, which we'll unimaginatively call the canonical remainder, and it basically looks like this: C of dt times mu of d by dt. And then there's the moment you have a non-constant vertical metric, there's basically a mean curvature form of the orbits you have to tack on. The moment you're non-abelian, again, there's a term involving structure constants that you have to tack on. And in the commutative case, this really is encoding somehow the moment of your clever connection with, relative to the G action, in fact the shape operator of the orbits, and various other bells and whistles. So in many examples, you need to actually subtract by this non-trivial term. So you can take your G spectral triple, you can make sense of what it means to be locally free. And now I'm running fantastically out of time. So let me say what do I mean by a principal spectral triple. So we have a vertical part, we have a horizontal part. How do you know that we can decompose and in the way and get a well-defined, smooth orbit space that pieces it together as we want? So this is what we need. So we have our G spectral triple, we have our vertical Clifford action, we have a remainder. And we say that all of this data gives us a principal spectral triple whenever basically the Peter-Weyl theory of this algebra sort of interacts nicely with the Peter-Weyl theory of the unitary representation H. Whenever the G invariant elements of H are, in this sense, sort of essential for the representation of this sort of vertical algebra. Whenever, I know this is where things get interesting, especially for some of you. If you take this DH, this is differentiation of the horizontal direction. And so supercommutation with DH is going to be some sort of horizontal exterior derivative. And so what this needs to do is satisfy something called the strong connection condition. So, which turns out to be quite important. And then finally, this is a massive simplification, but this is saying all this, you need a compatibility with C of dt. And in this particular case, amongst other things, this is telling you that we are this totally geodesic orbit situation. The orbit-wise shape operator vanishes on the nose. And this you see in the wild, the canonical spectral triple for the irrational rotation algebra, or equivalently the non-commutative 2 torus satisfies this. The canonical spectral triple for S3 theta satisfies this. You move up, the canonical spectral triple for S7 theta as an SU2, principal SU2 bundles, it satisfies this. So this really is something you can see in the wild. So what does this give you? Why do you care? Well, for starters, you can break things apart as you should. You can split off the orbit-wise intrinsic geometry and index theory. There's a wrong way cycle that sort of riffs off of earlier work, for instance, of Charlotte Wahl, that really intrinsically encodes the intrinsic orbit-wise geometry and index theory. If you take this horizontal operator and restrict to the G invariance of H, this is giving you a spectral triple for the base without any vertical spin C assumptions. So this restricted operator encodes basic geometry and index theory, and gives you a particular spectral triple for the base, modulo vertical spin C. And then the supercommutator encodes two things. It encodes the orbit-wise shape operator, in general, the orbit-wise extrinsic geometry, and it encodes the principal connection. Because remember, the spectral triple encodes in particular non-commutative Riemannian geometry. When you have a Riemannian principal bundle and you have this G invariant metric upstairs, it gives you automatically a nice orthogonal complement for the vertical tangent bundle. It's giving you a principal connection automatically. So that's sort of morally what's going on. And over to the Y's, given that we're restricting to the circle case for today, this guy is encoding, it actually represents the extension class of A as a Pimsner algebra. So which is a cute thing. That said, when G is SU2, I have no freaking clue. And it will be interesting to understand when G is SU2, again, you get something in KK1 A super G, but what this means for something like S3 theta over S2, I have no idea. And so I probably don't have all that much time, so no time for actual gauge theory, but let me just say that you can go the other way again. So suppose we have a principal G spectral triple. Basically what I want to say is that you really can decompose and glue back together. So this really says it all. Once you correct by the remainder, you can really decompose on the nose in unbounded KK theory into a vertical component, this wrong wave cycle, encoding all the sort of orbit-wise information, this basic spectral triple that encodes everything that's going on in the base, and then you glue this via this connection. It's a Hermitian connection. And what's nice is that you don't need to deal with any Hilbert module, Hilbert C-star module frames or anything. There's a black box. You can feed in geometric natural examples and things get spat out without having to get your hands dirty with the technicalities of unbounded KK theory. So to cut to the chase, since time is really running out, let me just say that this sort of very quickly indicates where the gauge theory is coming in. You fix the vertical geometry, you fix the horizontal geometry, you fix the orbit-wise extrinsic geometry. And it turns out that by comparison with the commutative case, all that's left is the principal connection. That's the only thing that's sort of variable. So you can basically set up at least a rudimentary framework where you've frozen the vertical geometry, frozen the basic geometry, you've frozen the orbit-wise extrinsic geometry. And all that is allowed to vary in the end is really just a choice of principal connection. And so this gives you a sort of non-commutative notion, sort of spectral triple friendly notion of gauge potential, which is invisible in index theory as it should be. There's a notion of gauge transformation. And really what I want to say is that you have an affine space of principal connections whose space of translations is easy to talk about. There's a well-defined gauge group, which may be a little restrictive, but it's a good start, that has a correct affine gauge action. You can topologize things. And it does the job in examples. In the commutative case, you really do get everything on the nose except for an explicit group-wide cocycle, which basically encodes the failure of some underlying Clifford connection for your Dirac bundle to be completely gauge invariant. That's the only sort of fly in the ointment. No such thing as a free lunch in NCG. And then even if you look at something like the irrational rotation algebra, and this is something I'm exploring more in this work in progress, it's a trivial principal bundle. These cross products are trivial circle bundles in a very precise sense. You shouldn't expect any kind of non-trivial gauge theory, and yet you're getting, there's real, honest group cohomology coming up. That's appearing, especially this is particularly interesting. The interesting part of the non-commutative gauge theory is basically the first group cohomology of the rotation action on real value functions in the circle. And this is extremely sensitive to what theta is. So I think I've more than run out of time. I think I'll leave it at that. I thank you all for your patience and your attention.